Okay, so question 9. So here we're given an ellipse. Uh, this is the equation of an ellipse in two dimensions. And we're asked to do two things. One is to find a change of variables mapping the unit disk to this ellipse, and then use this to find a formula for the area. So let's do part one. So first, let's draw the ellipse. So what does it look like? Well, these A and B are the lengths of the axes. And so it's a set that looks like this. This is A, this is B, and this is the set E. And what we want to do is we want to find a mapping that maps a disk in the UV plane, called as D to E. So the natural thing to do here is to just map the boundary. So we want to, this is a transformation T of UV equals XY. And we want to find something that maps this circle to this ellipse, and it's sort of natural what to do from looking at the equations. So if we take x equal to AU and y equal to BV, then indeed the image of this set of points, so u squared plus v squared less than or equal to 1, because u is equal to x over a, v is equal to y over b. This corresponds exactly to the set x squared over a squared plus y squared over b squared equal to 1. You can also just do a sanity check. If you look at a point on the boundary here, this is the point 0, 1, it gets mapped to the point, this is the point 1, 0, it gets mapped to the point a 0. And then this point 0b gets mapped to the point, I'm sorry, 0, 1 gets mapped to the point 0b. And it's clear that this is a one-to-one transformation. Given any x and y, there's a unique UV that maps to it, and vice versa. So that's the change of variables. And now the second part is to use this to figure out the area of this ellipse. So E is really the region inside here. And we figured out how to calculate the area. So we're interested in the area of E, which is a double integral over E of 1 dA. And that's just a double integral over E of 1 dx dy. And now we want to write this as a UV integral. We want to relate this area to some UV integral, which is going to turn out to be the area of the circle. The change of variables formula says that this is a double integral over d of 1 times the Jacobian. And so what we have to do to calculate this is to calculate the Jacobian. So let's just do that. So the Jacobian, well, maybe I'll just write down the matrix. Is this matrix xu, xv, yu, yv. So this is a very simple change of variables. Xu is just a, xv is 0, yu is 0, yv is b. So this is just ab. And so we're going to take the absolute value of this. A and b are positive, if I'm thinking of them as the axes of this ellipsoid. And so this just becomes a double integral over d of 1 times ab du dv. That's just AB times the area of D. And the area of D is pi r squared because it's a circle and r is 1, so it's just pi AB, which is what we wanted. Okay, so I mean, this is a fairly simple change of variables. The reason I assigned this question is just to test whether you know which order to do the mapping in. That's the most common thing to get confused about. Do you map from UV to XY or XY to UV? And so. Okay, number 10, another integration problem. You want to find the volume of a certain region. defined by three surfaces. So it's inside the sphere of radius 2 at the origin, above the z equals 0 plane, and below the z equals x plane. So let's start by drawing a picture before setting this up as an integral. Usually that'll guide us as to what kind of integral we should try. So let's draw the axes. And then we have this sphere. X, Y, Z. And this region is above the z equals 0 plane, so it's above the xy above the xy plane. It's inside the sphere, and it's below the plane z equals x. So what does the plane z equals x look like? Well, in the xz plane, it's just a line. Maybe it looks like this, and we're asking for the region that's between this xz plane inside the sphere and above the xy plane. And so really, it's going to end up looking something like this. Right? Because this xz plane is parallel to the y-axis. Okay, maybe I should draw that line here. Something like that. Okay, so it's this wedge-shaped region that we're looking for, and we're interested in finding the volume of this region. Okay. Okay. So now, this upper part is, maybe I'll do it in green. So thinking green, this is the xz plane. And so what sort of integral should we use? So, I mean, we could try a double integral. If we identify this as, the volume underneath the graph of some function, or we could try a triple integral if we identify this as a type 1, 2, or 3 region. Both of those will work. The simplest way, I mean, there's several possibilities. If you want to view this as a graph of a function, we wanted to view this as a function of x and y, maybe a function of y and z, or a function of x and z. And you should really ask yourself this question before proceeding. And I think x and z have a special role in this problem, right? Namely, both of these planes are just lines in the xz plane. So if you actually look at the shadow of this region in the xz plane, it's very simple. So let me mark it in blue. The shadow of this region in the xz plane is just this wedge here. Okay, so the shadow in xz plane is actually just the set z greater than or equal to 0, x less than or equal to z, and x squared plus z squared is less than or equal to 4. So the xz plane is a plane where y equals 0. And so this is the blue region, right? So I'm going to call this region D. These are the equations describing D. Okay. So it's a fairly simple shadow, and you can see that the sphere just sort of curves inward as you move away from the xz plane. And so actually we can write the sphere as I'm sorry, we can write this region as a type 3 region. Because it's sandwiched between the graphs of two functions of x and z, where x and z are allowed to lie in this domain D. So what are those functions? So the question you have to ask yourself now is that if I'm at some particular point in D, so I fix some value of x and z, what's the range of y that I encounter? And the answer to this is given by looking at the equation of the sphere. So we know that x and z lie in this region D, and y lies between the two boundaries of the sphere that you get when you draw a straight line through that point. So the picture is something like, if you draw this line, how far out does it go in both directions? And the answer is, well, it goes to the boundary of the sphere. So y is at most square root 4 minus x squared minus x squared, and at least minus square root 4 minus x squared. minus c squared. Okay. So this is actually the tricky part, setting up the integral correctly. But once you've drawn this picture, you can clearly see that this wedge, this region that I'm interested in, is a type 3 region. And then I know how to compute the volumes. Therefore, the volume, which is just the triple integral over this region E of dv, is just going to be the double integral over d times the and then of the single integral between the bottom limit for y and the upper limit, so minus square root 4 squared minus z squared, then square root 4 minus x squared minus squared, dy dz dx. Okay, so that's the integral we need to compute, and now just a matter of cranking it out. So let's do that. So the innermost integral is really straightforward. It's just an integral of 1, right? So let's just get that out of the way. So this will be just 2 square root 4 squared dz dx, where again d is this wedge-shaped region in the xz plane. So x is at most z, that's why you get, this is the line x equals z. Z is greater than or equal to 0, and x squared plus z squared is at most 4. Okay, so this is the region D. It's a sector of a circle of radius 2. Okay, so now let's think about how to evaluate this. Well, if you look at this picture, this should scream out polar coordinates, right? I mean, this is sort of annoying, but we've seen this many times. This region is, and both the region and the function will become nicer if we switch to polar coordinates. So let's describe this region in terms of polar coordinates. So what's the range of R? Well, R can go from 0 to 2, because a circle of radius 2. And what's the range of theta? So what's this angle? Well, this is a line x equals z that makes an angle of pi over 4. So really, this is just a polar rectangle. Theta goes from 0 to pi over 4, and R goes from 0 to 2. So switch to polar coordinates, we see that this is just an integral over a polar rectangle. So the order doesn't matter since it's a rectangle. You have 2 square root 4 minus r squared, so x squared plus z squared equals r. So, I mean, explicitly what I'm doing is I'm taking x equal to r cosine theta z r cosine theta. And now the important change of variables, when you switch from Cartesian to polar, you pick up this extra r factor. So it's r d theta dr. Okay. So I've put the theta on the inside because this function is trivial as a function of theta. So this is just a constant as far as theta goes. So if I compute the integral from 0 to pi by 4 of 1, I just get pi by 4. So it's the integral 0 to 2 of pi over 4 times 2 square root 4 minus r squared r dr. And now this is just a one-dimensional integral, which we have to evaluate. And one way to do that is use substitution. So let's just do the substitution. U equals 4 minus r squared. So then du equals minus 2r dr. If we do the substitution, then let's take the constants out. So we get a pi over 2 in the front. The limits become 4 and 0. And now we have a square root u du, but then there's a minus half that we pick up from here, right? So the rdr turned into a du. Okay, and that's something we know how to compute, so let's just compute it. So that becomes minus pi over 4 integral from 4 to 0 square root du, which is minus pi over 4 u to the 3 halves over 3 halves, 0 and 4, which is just calculate it out. So that's minus pi over 4 times 2/3. The 0 goes away. You get a minus 4 to the 3 halves. So the minuses cancel, and this should happen because it's a volume. So 4 to the 3 halves, that's just 2 cubed. So you get pi over 4, 2/3 times 2 cubed. Okay. Okay, and now, just to do a sanity check and perhaps to indicate a really slick way of doing this problem, let me write this in a slightly different way. So this is just 1/8 times 4/3 pi times 2 squared. Okay, right? That's exactly what it is. And what is this? This is the volume of a sphere of radius 2. So that's a familiar formula, pi cubed. But what's up with this 1/8? Well, another way to think about this 1/8 is this is just pi over 4 divided by 2 pi. And this, if you go back to what we're doing, this is, what are we computing? We're computing the volume of a sphere intersect a wedge. The wedge that's defined by the plane x equals z and z equals 0. And that wedge occupies an angle of pi over 4 in the xz plane, which is a 1/8 fraction of the total angle. So intuitively, it makes sense the volume of the wedge should be, proportional to the fraction of the total angle that it uses. This is that makes sense. Okay, so in this problem, you have to find. So there's a vector field. There's a force exerted by a charge at the origin. There's a vector field given in this form, and you want to. So the picture is, there's an electron at the origin. It's exerting some force. It seems to be inversely proportional to the position vector of the point, so it gets smaller as you get away from the origin, and it's directed along the position vector. I want to find the work done um, on an electron that moves between 2 points. So I'm just drawing these inaccurately, 2, 0, 0 to 2, 1, 5. And the question is, what's the work done? Well, so first let's turn this into an integral. So what's the work done by a vector field on a moving particle? Well, it's just a line integral. And in order to actually compute this, we need to parameterize the curve C. So let's do that. So the curve C is just moving between these 2 points. So we know how to do that pretty well by now. So it's 1 minus t times the starting point plus t times the final point. And so it just has a parameterization r of t equals 2t 5t, where t goes from 0 to 1. So that's a parameterization of curve C. And now I want to find this work, which is line integral. So that means it's integral from 0 to 1 of f of r of t dot r prime of dt. Okay. So I could now just start plugging things in. I could start plugging in, the field, start already plugging in the parameterization. But let me just plug in the field for now. So the field is just minus k, which is a constant that comes out front, r of t over magnitude of r of t cubed dot r prime of t dt. Okay, so there's some integral, and I could just plug everything and start computing it, but it might be slightly annoying because in this magnitude I have a square root. I'm going to get a square root of some polynomial. It's not I mean, you can just go down this path and do a, you can compute it, but I want to show you a slicker way of computing it, which is the observation that, the only annoying part of this integral is magnitude of r cubed in the denominator. If I could somehow get rid of that, or, make it simpler, I would get a simpler integral. And the trick here is to observe that the numerator, which is this r of t dot r prime of t, is actually uh, just the derivative of the squared magnitude of r. So, let's just calculate this. Is something we did early in the course. So what's d by dt of r of t dot r of t? This is just the magnitude squared. Well, by the chain rule, it's r prime of t dot r of t plus r of t dot r prime, which is just 2r t dot r prime of t. And this is kind of cool because this is exactly what appears in the numerator. So if I make this change of variables, uh, u equals magnitude of r of t squared, then this integral simplifies a lot. So let me do it on the next page. Or let me just do it on this page and then rewrite it on the next page. It becomes minus k. So the limits now become r of 0 magnitude squared, r of 1 squared. And I have this relationship that du equals 2 r prime of t dot r of t dt. That's what I derived in the other box over there. And so the integral now becomes just 1 over u to the 3 over 2 uh, du. You pick up a half because of the two change of variables. Okay, so now this is just the point is all the vector stuff went away. I got a very simple function, just 1 over u to the 3 halves. And now I can just evaluate it. So let me do that. So integral minus k over 2, integral from r of 0 magnitude squared to r of 1 magnitude squared, 1 over u to the 3 halves du. And now let's just plug it in. So you get minus k over 2. So r of 0 is a point 200. You get 4. R of 1 is a point 215. So if you add up the squares of those numbers, you get 30. You get u to the minus 2 du. And this is now just computed. So get u to the minus half, minus half, 34. And so if you work this all out, so this half cancels with the 2, you just get k times I guess 1 over square root 30 minus 1 over square root 4. And so, okay, I mean, that's k times 1 over square root 30 minus a half, which is some negative number, which is fine. The work done can be negative. But I mean, the nice trick in this problem is you could save yourself a lot of work if you use the vector product rule to find this nice change of variables. If you just plugged everything in, you would eventually be able to do it as well, but that's a nice trick, or it's a nice pattern to look for. Okay, so before starting this, I just want to say that in the last problem, I just realized I made a mistake in the arrows. So in the vector field, the arrows were going away from the origin where the charge was placed. But actually there was a minus k in there, so they should have been going in. They should have been going towards the origin. That makes sense. If there's a positive charge, it will attract an electron. And this also makes sense with why we got a negative work at the end. Because if the field is pulling the particle towards the origin and it's moving away, which is what it was doing, then the work should be negative. Anyway, let's move to the next problem. So here we're told that there is a surface. We're not actually given the equation of the surface. We're just told it has an equation of type z equals f of x. So what does such a surface look like? Well, if you were to just draw its trace in the xz plane, you would maybe get some curve. What this is saying is that since there's no dependence on y, the surface just looks like, you know, copies of this in both directions. Okay, I mean, I guess that doesn't look exactly the same. Let me try to, whatever. Okay, so this is every y equals c trace, it's the same. So we have the surface S. And now we're asked to show that for some specific vector field f, the line integral of f along every closed curve lying on the surface is 0. That seems kind of amazing. So the statement is, in the surface, you can have a simple closed curve C, and we're asked to show that for every such curve, that's infinitely many curves, um, the line integral of this vector field is 0 for every curve. And the hint is to use Stokes' theorem. So let's do that. So Stokes' theorem says that this integral is equal to the flux integral of the curl of the vector field f across the interior of such a curve. So, or across any surface that has this curve as a boundary. So we have to choose a surface with C as a boundary. So what's the natural thing to do? Well, let's just choose the part of S that's inside C. Let's call this S1. Okay, so S1 is now a subset of S, and its boundary is clearly C because C lies on S. So Stokes' theorem tells us that each of these integrals is equal to a flux integral like this. And our goal is to show that this thing is 0. So before we do that, let's think about how this could possibly be true, right? We want to show that this integral is 0, but actually we want to show that, all these integrals are 0. There are infinitely many such integrals. We want to show that they're all 0. So what could possibly be the reason that they're all 0? I mean, it's unlikely it's some symmetry argument or something because, it's true for all S1. So probably, one way for it to be 0 would be to show that the integrand itself is 0. So let's try to do that, or in any case, let's just compute these two vectors that appear in the integrand, the curl of f and the normal vector. So let's compute the curl. So this is now just a formula, so it's a determinant formula. Xe. So the curl has three components. If you just expand the determinant, you see that the first component is 0. Second component is minus c, and third component is also 0. Okay, so what that says is that this vector field at every point, at every point in space, its curl is pointing in only in the y direction. The x and z components are 0. Okay, so the curl of f always looks like this. That should already give you a hint. That looks like it's orthogonal to the normal vector of this surface, right? Because the normal vector is going to look like this. So the dot product might end up being 0, but let's just verify that. So let's compute the normal vector. So how do you compute a normal vector to the surface? We don't even know what the equation defining it is. Well, the surface is a level set of the function, g equals z minus f of x equals 0. And we know how to compute normals to level sets. They're just given by gradients. Here the n is the unit normal, but we know it must be parallel to, the normal, to any other normal, which is a gradient. So we know that n is parallel to the gradient of g, which in this case is, so partial with respect to f, which is minus fx, no dependence on y, so you get a 0, and partial z is 1. So now it's clear the gradient is parallel to a vector that's 0 in the middle coordinate, and the curl is 0 everywhere but the middle coordinate. So we have it. The curl of f dot n equals 0 everywhere on S1. And so that means that this integral is actually equal to double integral of S1 0 ds. And that completes it. Okay. Number 13, we're given a vector field in 3 dimensions. For what values is this conservative? Okay, let's sort that out. So, okay, this vector field depends on two constants a and b, right? So, okay, so how do you check whether a vector field in 3 dimensions is conservative? So we went over a number of theorems. Independence of path, that's not so easy to check because there are all these paths you have to check, but the vector field is defined on all of R3, which this one is because the entries, it's just polynomials, then f is conservative if and only if the curl of f is identically 0 on R3. So let's compute the curl of f. What's the curl of f? We have this formula, and this is where the constants come in: ay squared, 2yz, and by squared plus c squared. Let's just do this component by component. The first component, gonna have this determinant, so you're gonna get a 2by minus 2y. For the second component, we actually just get 0. And for the third component, we get 2y minus 2ay. Okay. And so in order for the field to be conservative, this thing has to be 0. And when does that happen? Well, that happens when all the entries are 0, and that happens when a equals 1 and b equals 1. So for a equals 1 and b equals 1, this vector field is conservative. That's part 1. Part B is to find some f so that the vector field is a gradient of. And now we know that this vector field, we now found the values of a and b for which it's conservative. There's only one value. The vector field is y squared 2yx plus c and y squared plus c squared. And if this thing is equal to the gradient of f, then we actually get three equations. Right? The first component of the vector field is fx, second component is fy, third component is fz. We get these three equations. So let's write down these three equations. Okay, so now let's use these three equations to find f. So what are the three equations? First one is fx is equal to y squared. The second one is fy is equal to 2yx plus c. The third one is fg is equal to y squared plus. So what are the steps? So we're going to use partial integration. Get more and more information about this hidden function f. So let's integrate the first one with respect to x. I get that f has to be integral of y squared dx, which is xy squared plus g of yz, which is some unknown function of y and z. And the reason this has to be there is that differentiating with respect to x will kill any function of y and z. Okay, I didn't find x, but I found some information about x. It has this form, and now I just have to find g. How am I going to find g? Well, I'm going to plug this into the second equation. So to plug this into when I plug this in the second equation, that means that partial derivative of this quantity with respect to y has to be equal to the right-hand side, which is 2y times x plus c. Let's do that. Partial derivative of this quantity is equal to, so what is that? That's 2xy plus gy. This has to be equal to 2xy plus 2yz, according to the second equation. And this is good because now I can cancel these terms, and I get that gy is equal to 2yz. We'll just continue here. Which I can integrate in y to get that g is equal to the integral with respect to y of this quantity, which is y squared z plus some function h of z, some unknown function of z that I still don't know. Okay, so now I've made progress. So now actually I know that my f is equal to xy squared plus y squared z plus some function h of z. I just have to find it. And not surprisingly, the way I'm going to do this is by plugging this into the third equation. So plugging this into the third equation, differentiating this in z, what do I get? I get that the first term goes to 0, second term is 2yz. I'm sorry, not 2yz. Second term is y squared. I'm differentiating in z plus h prime of z. It's the derivative, univariate derivative of h with respect to z, has to equal y squared z squared. And so this means that h prime of z is equal to z squared. And so h of z is equal to z cubed by 3. And combining all this information, I have finally found out what f is. I'm going to write it in the corner. So f is equal to xy squared plus y squared z plus c cubed by 3 plus a constant. Yeah, so I say I have to always have to add a constant. Okay, so that's a function. I mean, that's a class of functions. It asks for one function, so okay, let's just set the constant equal to 0. That's one function for which the vector field capital F is the gradient of F. Okay, and now for the last part, which is very conceptual. So it's saying, I mean, it sounds kind of crazy. It's saying find some surface. We don't know what this surface is going to be, with the property that if you have any 2 points on the surface P and Q, then the line integral of this vector field, the given vector field, along well, any path uh, is 0, right? So okay, so how can this possibly make sense? So well, I mean, the hint is already that the path is not specified, right? So only the endpoints matter. And the hint also, you should think of this from the previous part of the question. I'm interested in computing this line integral between points P and Q. In the previous question, I just discovered that the vector field is a gradient of some function little f. So the fundamental theorem of line integrals says that line integrals are independent of path. And in fact, the value of the integral is just f. The difference is value of the potential f between the 2 points Q and P. And what I want is I want a surface with the property that this is always 0. So what that translates to is I want a surface where for any 2 points, the value of f is little f is 0. I'm sorry, the difference between the values of little f is 0. In other words, little f is constant on the surface. We already have a name for this. It's just a level surface. So just be any level surface. For example, just f equals 1. Okay. Okay, so in this question, you're given a parameterized surface. You have to do two things. One is find the surface area, and the other is find a parameterization of the boundary curve with the correct orientation. So let's start with the surface area. So we're given this explicit parameterization, r of uv is equal to u comma v comma uv. And so what this looks like is that there's a uv plane where parameter domain is just a disk, and R is mapping this into a three-dimensional surface. X is just u, y is just v. So actually this surface is actually the graph of a function, just the function uv, or the function xy, in the xy plane. So what's it going to look like? Well, at x equals 0, at this point, at the point 1, 0, it's going to be at the point 1, 0, 0. And then as you move around the circle, it's going to look something like this. So at this other point, 0, 1, it's going to be at 0, 1, 0 again. And then it's just going to go around in a circle, but the height is going to be the function xy. So it's going to end up looking like a Pringle, actually. I don't think I can. I don't think I'm going to be very good at drawing that, but something like this. Okay, so that's the surface S. And the first step is find its surface area. So we know how to do this. So surface area is just the double integral with respect to surface area of 1. And the change of variables is something we've discussed many times. This is just the double integral of RU cross RV dA over the parameter domain. So let's now calculate this. So RU is the vector 1, 0, V. RV is a vector 0, U. RU cross RV is this vector, which let's see. So the first component is minus V. The second component is minus U. The third component is 1. So the magnitude is just square root 1 plus U squared plus V squared. So it's going to be double integral over U squared plus V squared 1 of square root 1 plus U squared plus V squared du dV. And this, again, this looks like you should do it using polar coordinates. So let's switch to polar. The circle becomes very nice in polar coordinates, just a polar rectangle. You have 1 squared, 1 plus r squared, r dr dθ. And okay, I mean, this is something you can easily do. We've done too many similar integrals in this exam for me to do another one. So I'll just tell you what the answer is. If you do this correctly, you get 4 pi over 3 squared. Okay. Okay, and now the second part is to find a parametrization of the boundary. So the boundary curve is this C, and I want to find a parametrization that's oriented positively with respect to the orientation of S given by RU cross RV. So the orientation of S given by RU cross RV is this, and the Z direction is pointing up. So this is the orientation where the surface is oriented up like this, normal vector. And so if I want to find an orientation of the boundary that's positively oriented, well, when I walk along the boundary, then with my head up towards the normal, the surface should be to the left. And so that orientation should just be like this. And that corresponds to going around the circle counterclockwise. And so for part B, what I need to do is find uh, an orientation of the circle going a parameterization of just the circle in the UV plane going counterclockwise. And then map it through this parameterization R to get a parameterization of the boundary, right? Because the boundary of D, the boundary of the parameter domain, gets mapped to the boundary of the surface. That's the conceptual fact that I'm using here. So let's do that. Yeah, okay, so let's now think about this. So the boundary of the parameter domain, positively oriented, it's just a circle. So it's just cosine theta sine theta, where theta goes from 0 to 2 pi. Now the point is that R maps the boundary of D to the boundary of S. And so a parameterization of the boundary of S should just be R applied to this parameterization of the boundary of D, which will give cosine theta sine theta cosine theta times sine theta, where theta is from 0 to 2 pi. And again, this is positively oriented by the geometric reasoning on the previous slide. We figured out that the normal was going up, so we should walk counterclockwise. Okay, so in this question, we're given an oriented surface S, which is the graph of this function f, above a domain D in the xy plane, which is just a circle, and the surface is oriented in a particular way. And the goal is to compute the flux of this vector field, fairly annoying looking vector field, f through S. So let's start by drawing a picture. So here are the axes. So S, I mean, you may recognize this by now. This is an upside down parabola. So maybe it looks something like this. And S is just a piece of this that lies above the unit disk. So there's a unit disk here. And S is maybe this piece. I mean, okay, those circles don't exactly line up, but this is S. So S is the top, part of this paraboloid. And S is oriented upward. So the normal vector looks like this. And we're interested in the flux of F across S, which looks kind of annoying at the outset because F itself looks pretty complicated. And so we want to do this using the divergence theorem. So the divergence theorem is a theorem that applies to closed surfaces that are boundaries of solid regions in space. And S is not of this type. S is actually an open region. It's not the boundary of anything. And so the idea, as we discussed in class, would be to add a piece to S to convert this into a closed surface, which is the boundary of a three-dimensional region, and then apply the divergence theorem. So the natural thing to do is to look at the base of S. I'm highlighting in blue. Let's call this S1. That's oriented downward. And now S union S1 is the boundary of a solid region that's enclosed by them. It's this top piece of this parabola. Let's just write down what it is. Just explicit. It's the region E where it's a point out of all points x, y, z, so that x, y, I in D, so let D be this circle bottom, and z lies between um, uh, yeah. So what does z lie between? So we have to figure out what value of z this cylinder x squared plus y squared equals 1 intersects the paraboloid. So let's figure that out. Squared plus y squared 1. This implies z equals 2 minus x squared minus y squared equals also 1. So this intersection is happening in the plane z equals 1. So the values of z inside the solid region E, z lies between 1 and 2 minus y squared. Okay? So E is this region in here. And now we're interested in calculating the flux through S. What does the divergence theorem tell us? Well, it tells us that the flux through S union S1, which is just the same as the sum of the fluxes of F through um, uh, through these pieces, is equal to the triple integral divergence of F over the interior E. So in particular, this means, so this is what we want. And this theorem says that, well, if we can compute the other two pieces, we can just subtract them and get what we want. So let's give these pieces names. Let's call them let's call them 1 and 2, Roman numerals. And let's just go ahead and now compute them. And again, the goal is that the thing we want to compute looks really annoying. I mean, the surface is not that simple. It's a paraboloid. The vector field looks kind of insane. Doesn't look like any fun. And the point is, we've now reduced it to computing two things which might be easier. They will actually turn out to be easier. Okay, so now let's just compute these pieces one by one. So the first piece is the flux of F through S1, where S1 is this disk at height z equals 1 oriented downward. And okay, let's just write down a parametrization for that disk. So again, it's just a disk, but it's translated by 1. So natural parameterization is just r of x, y 1. We just lifted it off the plane, where x and y lie in domain D, which is just the usual disk. The normal vector in this case is just 0, x1. -1. It's pointing straight down. What's the change of variables? Well, Rx is just 1, 0, Y is just 0. And so magnitude of the cross product is 1, which means that ds. And you don't have to do this every single time, but whenever you have a flat region parallel to a coordinate plane that's parametrized by the coordinates in that plane, then ds equals dA. Okay, so now we can write this more concretely as a double integral over d of f of r of y dot minus k dA. And so what that means is, well, in this dot product, only the last coordinate of f matters. So we don't care about all the other stuff. The last coordinate of f is 7 minus z minus 2xz over 1 plus 3y squared, but z is equal to 1. So when you plug this in, you get that this is minus 7 plus 1 minus 2x over 1 plus y squared dx dy. And this integral sort of conveniently breaks into two terms. So the first term, let's pull out the constant term. So it's going to be minus 6 times the double integral, let's try d dx dy minus the double integral. And now let's write this in iterated integral. So y goes from minus 1 to 1. X goes from minus square root 1 minus y squared to square root 1 minus y squared of the quantity 2x over 1 minus 1 plus y squared dx dy. And the reason I'm writing it this way is that it becomes very clear that the second integral is 0. And the reason it's 0 is just look at the inner integral. So the inner integral is just an integral in x. So 1 plus y squared, the 2 over 1 plus y squared is a constant. It's an integral from minus square root 1 minus y squared to square root minus y squared x dx. And so by symmetry, because x is an odd function, this is just 0. Or if you just want to compute it, x squared over 2 and plug in the limits, you get 0. And so actually this integral just vanishes, this becomes 0. And so the only thing that remains is the first part, and the first part is just minus 6 times the area of the disk, which is minus 6 pi. So the first integral that we're interested in computing is just minus 6 pi. Okay, so to finish this, we now have to compute the last piece, which is the triple integral over E of the divergence of F. So let's compute the divergence of F. So F is this crazy looking vector field. Maybe taking the divergence will make it a little bit simpler. Okay, so the divergence of F is so it's a partial with respect to x of the first component, that's minus 4 plus 2x over 1 3y squared, plus the partial with respect to y of the second component, that's 3, plus the partial with respect to z of the third component, that's minus 1 minus, again, 2x 3y squared. So this annoying stuff just cancels out, and you just get a number, minus 4 plus 3 minus 2 minus 2. Unfortunately not 0, but minus 2. So that's not so bad. And again, this region that we're interested in is given by x and y lie in the disk, and z lies between 1 and 2 minus x squared minus y squared. So now this integral is just triple integral minus 2 times the triple integral dv over d. So that's just a volume. And I can write that as an iterated integral. It's minus 2 times the double integral over d. So just put a d here. 1 to 2 minus y squared d y dx. That's minus 2, or I guess I should write dA using notation, and that's just double integral over d of 1 minus x squared minus y squared dA, which I can now switch to polar coordinates. So in polar coordinates, it's an integral of 0 to 1, 0 to 2 pi, 1 minus r squared r dr d theta, or r d theta dr. So I want to integrate theta first. And this is a constant in terms of theta, so it just becomes 2 pi times integral 0 to 1 r minus r cubed dr, which is 2 pi times r squared over 2 minus 4 over 4, evaluated 1, 0, which is just pi. So it's a half minus a 4. Okay, and now finally we can put all the pieces together. We have the integral that we want. Minus 6 pi is equal to pi. And what that means is that this flux that we want is just equal to 7 pi. Okay. Okay, so now we're at the last question of the exam. So this is a bit of a mouthful. Okay, so there's a broken wine bottle placed on the xy plane. It consists of a portion of a cylinder of radius 1 centered on the z-axis, and the bottom is this disk. And the broken part is this weird jagged path C on the top, oriented as shown. And there's some, fairly simple looking vector field given, and I'm asked to find the line integral of this vector field along this path. And so at the outset, if you look at this, this looks impossible because, I didn't even give you a parametrization of the path, right? It's just a broken wine bottle. It's not like I told you what function that broken part is. So this is the part that we want. And, if you didn't know any of the cool theorems in this class, you wouldn't know how to proceed. But the beauty of this is that we can use Stokes' theorem, turn this into some line integral that we actually do understand. So in this picture, what's a closed curve that actually I do know how to parameterize? Well, it's the bottom of the bottle, right? The circle in the plane. And so the idea is, well, let's define, let's try to find a surface, a two-dimensional surface, so that this curve C is part of its boundary, and the rest of its boundary is the bottom of the wine bottle, which I know how to evaluate. And then I'll be able to relate the two via the flux of the vector field across the surface. So let's make the sides of the wine bottle the surface S, sides of the cylinder, not including the base, just the sides with this jagged top. And now I want to make it so that the line integral above is positively oriented with respect to the cylinder. I want to think about what positively oriented means. So I want to choose the normal to S in such a way that when I walk along the top edge and my head is pointing towards the normal, S is to my left. And so if you think about that for a moment, you'll see that the orientation that does that is the inward orientation. Okay, so now C is positively oriented with respect to S. And if I took the base as well, then C would be the boundary of this. But actually, I'm going to do something even slightly more clever. I'm only looking at the sides. I'm not looking at the base. So S actually has a boundary that consists of two pieces. The other piece is the circle at the bottom. And if you want to make this positively oriented, again, you want to be walking in such a way that if your head is pointing towards the normal, the surface to your left should be actually going counterclockwise. Let's call this C1. And now, if you look at this, then C1 union C is the boundary of S. and it's positively oriented. Okay, so Stokes theorem works for surfaces that have a boundary that has two pieces as well. And I mean, if you want to derive this from the version for one piece, then you could just do a separate argument where you, um, I mean, I might as well just do it here right now. So, Stokes theorem says that the flux integral across the whole cylinder, across the surface S, including the base of the curl of F dot ds, is equal to the work integral of the vector field around C. Stokes theorem also says that the double integral just of the base of the curl of F dot ds is equal to its boundary. And let's orient this one going well, let's just orient this one going up as well. Okay, so this is equal to the the work integral around C1, actually minus C1 because C1 is going the opposite direction. And so now if I subtract these two things, what I get is that the double integral along S, which is the bottle with the base minus the bottle without the base, the curl of F, the flux of the curl of F, is actually equal to the line integral along C plus the line integral along C1. So you see that the sign got reversed because I subtracted. And this is the fact that I'm going to use to compute the line integral along C. Okay. So again, this is the thing we want, the line integral along C. And I've now used Stokes' theorem to express it as a flux integral across S, the side of this bottle, and a line integral along C1 oriented negatively, which is something that I oriented, clockwise, which is something that I understand. So again, let me just now call these things 1 and 2, and let's just go ahead and compute them. Okay, so in the first integral, I'm just interested in this very simple curve, C in the xy plane. It's just a unit circle oriented clockwise. And I want the work. This is C1. Actually, it's called C1. So, I could do this directly. I mean, my vector field F is not so bad. Has components minus y, 2x, and z. So I could just plug it in and, crank it out, but, why not just use, well, okay, why not use Green's theorem? So the first thing to notice is that this is equal to, if I have some parameterization of C1R, this is equal to F of R dot R prime of P dt. Let's say the parameterization of 0 to 1 or 0 to 2 pi. And the first thing to observe is that this R prime of P, which is the velocity, well, whatever it is, it's something, something, and 0. It has no component in the z direction. And so what that means is that the z component of this vector field is actually totally irrelevant, right? I mean, it's just going to get multiplied by 0. And so this integral is actually equal to the integral along C1 of a two-dimensional vector field, what I would get if I ignored the first component. dot r prime of dot dr. Let's say. Okay, and now this is a two-dimensional problem, and we can apply Green's theorem. So I just did that so I could reduce this formally to a two-dimensional problem. And now Green's theorem tells me that this line integral is equal to the area integral of qx minus py, which in this case is 2 plus 1 dA on D, where D is the interior of this, which is just a circle, but there's a minus sign because in Green's theorem, you need a positively oriented curve. This is negatively oriented. But this is great. This is just negative 3 times the area of the circle, which is just negative 3. Okay, so that was easy. We just observed that it's a two-dimensional line integral, and we used Green's theorem, and it was a circle, so we just got the area. Okay. Okay, and now we're down to the second part. So what was the second part? The second part was the flux of the curl of F across this jagged bottle, side of the bottle, negatively oriented. Okay. Okay, so again, this might look a little mysterious because again, we don't exactly know what S is. The top of it is jagged. But maybe let's just see if something nice happens. So again, the thing we're integrating is the curl dot to normal. So let's compute these things. So what's the curl of F? Well, times now. It's a determinant minus y 2x minus y 2x and e. And let's calculate that. So the first component is 0. The second component is also 0. The third component is 2 plus 1, which is 3. So the curl is something that's actually is very simple. It's a constant, and it's always pointing in the z direction. So the curl looks like this. And now already you see what's going to happen. The curl is perpendicular to the normal, so the flux is going to be 0. But let's just do that formally. What's the normal vector? Well, the normal vector to the surface, I mean, from the picture, it looks like it's in the xy plane, and that's all we really care about. So, we don't actually, I mean, we could derive some expression for it, but we don't even need that. The only thing we need to observe is that the normal vector has no component in the z direction. Okay, because the side of this cylinder, I mean, it's a cylinder. The cylinder is the surface x squared plus y squared equals 1. You could also just compute the normal. You could compute the gradient, right? It's the surface x squared plus y equals 1. The gradient of this function, so this is g, gradient of g is just 2x, y, 1. And so if you normalize this, I'm sorry, 0. So if you normalize, it's going to have a 0 in the last coordinate, right? So if you combine these two things, then that's it, right? So therefore, curl f dot the normal vector is going to be 0 because the first two entries of the curl are 0, and the last entry of the normal vector is 0, 0, 0 plus 0 plus 3 times 0, which is 0. And so actually this integral is just 0. The flux integral is 0. Finally, we now just combine all this information to get what we wanted. So the work integral we're interested in along the jagged piece, minus 3 pi equals 0. And so the thing that we wanted must be just equal to 3 pi. Sorry, I guess I'm putting these circles in some places not. I'm not going to insist on it. It doesn't matter. It just indicates that it's a closed integral. The answer is 3 pi. And that's the exam. So yeah, let me know if you have any questions. Please post them on Piazza.